Okay, so good afternoon, everybody. Let's start our class today. Last time we were in the middle of the big example, so today we're gonna wrap up that example. Let me for the continuity of our discussion, let me show you what we got. Okay. So first of all, this is an example that we work on. All right, so that's the slide 44 of our module 4. So we have a process of 5 resources. Think about this as a restaurant. It is open for 8 hours per day, right? And the restaurant serves 3 different products or dishes, A, B, and C. And we know the demand per day. That's why all of the calculation later on are per day, right? And then we need to draw the process flow, which we did last time, and carry out process analysis. So we are in the middle of the second task that we have right here, right? All right, let me check if you have any question. Okay, good. So let me show you the class notes too. We shared. Okay, so last time, right, after we talk about the lead time and the required production time, then we went to that example, right? So there are 3 products, A, B, and C. We know the demand, and we assume that the proportions of them are fixed. So it means that for every 4 ice creams, we're going to sell 5 burgers and 6 fries, right? So we assume that these proportions are fixed. The second thing is now we have to deal with 3 different products. And to deal with different products like this, then we have to find common things among all of those, right? That's why we would choose a common flow unit to be the minutes of work, because all the food items will require time, right? So that's a common among all of the food items. So that's a minute of work. And last time you already saw that, right? We already drew the process flow diagram. So what we are doing here is very similar to question 24 of the homework and also the part 3 of the project. So in the homework question, please feel free to draw something similar in a similar way. Of course, the arrows, what skips it is, you have to be very careful about it. And please put the triangles, right, in the chart, in the graph, to denote that there might be some wait time between the stations or between the activities or steps. Right, so that's the graph. And we did some calculation here. So the first part of the table just tells us the technology of the restaurant, right? So the processing time tells us how fast we are with our cooking process. The number of workers is not part of the technology matrix. The technology matrix is the processing times down here. So if we have 1 worker, then that's going to take that many minutes, right? But if we have 2 workers, then they can share the work and cut down the minutes by half. But by the process design and product design, right? This is how much it takes, how much work time it takes to process each of the dishes through each of the stations. All right, so that's a technology matrix. The second one is the supply matrix, where we calculate how many minutes of work that each of the stations can render, right? We do that per hour first, and then we scale it up by 8 hours per day, right? Then we have these numbers. So again, these numbers are the following. At station number 1, the 2 workers over there can render, can offer, can supply, can dedicate 960 minutes of work per day, or 960 minutes of service to the kitchen work or to the restaurant work, right, per day. And then because it's station 2, we also have 2 workers, so those 2 workers can also provide 960 minutes of work per day. Station 3 and 4, only 1 worker each right? So that's why we only have 480 minutes per day. And we go back to 960 at 5 because there are 2 workers over there. Okay, so that's very crucial, right? Now we know how much work that each of the station can offer to the restaurant work. All right, so that's the supply matrix. Then logically we would have the demand matrix, right? And that's where we have next here. So we have the demand for ABCs. Here we write out how many ice creams require work out of station 1, 2, 3, and the station 4 is a fryer. So that's why the ice cream do not require any work out of 4, right? So no work out of 4. And then going back to 5, we have 40 units of ice cream again. For the burgers and fries, they require works out of station 1 and 2, but because 3 is an ice cream machine, so the burgers and the fries do not require any work out of the ice cream machine, and that's why we have that 0 and that 0. All right, and going back to the same number like before. Okay, so in real life, if you apply this model to real life process, you might see zeros, right? It's not a surprise because by the nature of the process, by the nature of the products, or by the design of the products, that's what we had. Sometimes they will skip the unnecessary activities, right? So that's the physical units, and then we convert the physical units to the minutes of work. So right, if it takes 5 minutes to process one ice cream through station 1, we write that 5 minutes per ice cream right here, and there are 40 units of ice cream. Then station 1 are required or would have to work for 200 minutes to process all of the demand through, right? And that's for the burgers. That's for the fries. We calculate these minutes of work required, and then we add them up to have the total workload, right? So eventually, where the total workload is another crucial role. So that's why we do all of these in red. The total workload here is 750 minutes of work per day, right? So to process all those 40 ice cream, 50 burgers, and 60 fries through station 1 is required to work for 750 minutes per day. And then that's station 2, 3, 4, and 5, right? So that's what we have last time. We earlier we calculated the capacity, the supply, how much work the workers can provide, right? And then now how much work is required is required so that the workers can process all the orders through. So the next logical step is we compare this workload with that capacity, right? To see if we have enough capacity to handle the demand or not. Or in other words, we want to check if supply is up to the task of the demand or not. Okay, so let's go and then work on the notes. Just a continuation of what we have earlier. And again, what we are doing is very similar to question 24 in the homework. By the way, I just posted the link to submit the question 23, 24, and 25, right? So today we finish up question 24. On Wednesday, we cover the topic of question 25. So by Friday, I hope that everybody is ready with the remainder of the question. I mean, the remaining question, 23, 24, and 25. Does anybody have a question for me? You're good so far with the information? Okay. Good. So we are still in module 4 about process. This question, let me check. Oh, no. Process analysis. And in this module, we have, so now the big topic that we are at right now is level 3 analysis, right? What it means is we are looking at processes with level 3 analysis is processes with multiple steps and multiple flow unit types, right? Okay, so the example that we are looking at is so we have the example here is the restaurant example. This is module 4 and slide 44. So we just continue the table that we got last time. For me, I need to expand the table and do the frame, right? But for you, you just make the table longer. So we have resource 1 and 2, 3, 4, and 5. And now we know the demand and supply, right? Then we compare them by calculating the implied utilization. Oh, Matthew, we got a question about that. Implied utilization. You can try to make the ice cream by yourself, but you need to be very, very careful with it because the oil is hot, right? You don't want to drop the ice cream bowl into the oil. You should.
Do they have it all year round?
Yeah, or you use some kind of basket, cooking basket, okay, a small one like the tea or the something, the filter. So you put the ice cream in it, dip that the whole thing into the dough, and then dip the whole thing gradually into the oil. But you need to be very careful, okay? Very careful. The hot oil might splash out and then may hurt you. Okay, so implied utilization is calculated as the following. Let me remind everybody that IU equals what? IU equals the workload or demand divided by the capacity. All right, so we already calculated the workload, right? So I just going back to what we got last time and just copy the values here. At station number 1, the required workload is 750 minutes per day. And then we divide that by the 960 minutes capacity per day, right? Remember, there are 2 workers at station number 1. So those 2 can work for 960 minutes per day. And then based on the demands of the ice cream and burgers and fries, we calculate the required minutes of work at 1 is 750, right? So we take demand or workload divided by the capacity. So that's the first station. The second station, we're gonna have the workload of 620. Whereas the capacity is 960. The third one is we take 600, and the capacity is 480. Right? We got both of these numbers from the previous work that we got it last Wednesday, right? So the required the total workload divided by the capacity. And then at station 4, we will do 330 divided by 480. And at station 5, we do 900 divided by 960. Right, so what do we have here is the following. Let me write out the first answer and let's discuss the number. So 78.13%, right? So based on the equation here, what we see is the following. The workload of the demand is 78% of the capacity, right? So it means that we do have enough capacity to handle the demand at station 1. Right, so 78.13%. So we can do it because we have enough people to do it. And then at station 2, we have 64.58%. So that's only 64% of the capacity, right? So we have enough capacity to handle that demand. But then at 3, we have 125%. Think about it. We take the workload, we divide by the capacity, we have 125%. So it means that the workload or the demand, right, exceeds the capacity by 25% of the capacity. So that's the meaning of that number, right? So it means that at 3, we do not have enough capacity to handle the demand. And then at station 4, we would have 68.75%. And then at 5, we have 93.75%. Right, so all of these are the IU. It tells us the demand pressure. So the demand pressure here is not too much, or here and here, they are not too much because we do have capacity to handle the demand, right? But the demand pressure right here is too much. The demand exceeds the capacity. So think about it, if we ram the ice cream, the burgers, and the fries through the kitchen, then they can easily go through 1 and 2. But then they will get bogged down at 3. Some of the units cannot go through because they do not have enough people to handle the demand, right? So so that's why the demand here exceeds the capacity. And then after that, the items can go through because 4 and 5 can handle it, right? But now we realize that number 3 is our bottleneck, right? Because we do not have enough capacity to handle the demand over there. And that resource limits the flow through the whole kitchen. So that's our bottleneck, right? Let me make a note here. So for a complex process like this, the only way to find the bottleneck is to look at the IU, right? So for a complex process like this, the bottleneck is the resource with the highest IU. Okay, what does that mean? So if all the IU are below 100%, let's take that first example. Then even though they are all under 100%, but one of them will have to be, at least one of them will have to be the bottleneck, right? So just look for the highest IU, then we can identify the bottleneck resource. Or if some of them are more than, some of the IUs are more than 100%. In this case, we only have one IU, more than 100%, but in other cases, right, we might have multiple resources with IU greater than 100%. But then even though in that case, then we just look for the highest column, then we can identify the bottleneck, right? So that's, the bottleneck is the resource with the highest IU, no matter what the what values IUs might have. You just look for the highest column, then you can identify the bottleneck. Right? So that's the first note here. The second note here is the following. In this case, the restaurant does not have enough capacity to accept all the original demand, right? So it means that we have to say no to some of the orders. So the restaurant does not have enough capacity to handle all demand. All right. So if we cannot handle all demand, then we have to say no to some of the orders. So we can only accept partial demand. So for that partial demand, we're gonna come up with a new concept for the demand acceptance ratio. So this one is called
Professor, can you go back one more?
okay. Let me go back to the previous slide.
Sorry.
Yeah, if I'm a little bit too fast, please slow me down. That benefits the whole class. That's a good thing to do. Good, see. Okay. So let's continue. So now, because we cannot handle all the demand, we have to accept only partial of the total demand, right? For that, we will come up with a new concept called the demand acceptance ratio. Or DAR, right? So there are two scenarios, or there are two cases that we can determine the DAR. In the first scenario, if demand is smaller than or equal to capacity, right? How do we know demand is smaller than or equal to capacity? This is a complex case. To know it, you have to look at all of the IUs. So if all IUs either smaller than or equal to 100%, in that case, demand is smaller than or equal to capacity, right? So if demand is smaller than or equal to capacity, then we're gonna accept all of the orders. We accept all the demand because we do have enough capacity to handle all of the orders, right? So in that case, the equation for the DAR is the following. So DAR in that case is gonna be 100%. We accept 100% of all orders. That's what it means, right? But if in the second scenario, so that's the first one, that's the second one. But if demand exceeds capacity, then in that case, oh, by the way, what does that mean by demand exceeds capacity? Then at least one IU greater than 100%. And that's what we have in our current example, right? But resource number 3, the IU exceeds 100%, which means that demand for this restaurant exceeds the capacity of that restaurant, right? Think about that as a bottleneck. So the demand is more than the bottleneck now. So in that case, we cannot accept all of the demand. We can only accept partial of the original demand. So DAR in that case is equal to 1 divided by the IU of the bottleneck. All right. So 125% is more than 100%. So now we have to scale it down back to 100%. So in that case, we're gonna do the following. Using the equation, we take 1 divided by IU of the third resource, right? Because that's the bottleneck. And that is 125%. Or 1 divided by 1.25. If you calculate it, it's gonna be 0.8 or 80%, right? What it means is, in this case, because demand exceeds capacity, we can only accept 80% of the orders, okay? So if you remember the Popeye chicken sandwich or something like that, it came out like 3 years ago. At that time, a lot of customers stay in a long line like this to order the chicken sandwich, right? And not all of them would get the chicken sandwiches because it's too much for the restaurant to cook. So some of them had to go home empty, and then they came back the next day, right? So in this case, it's going to be the same. So because we do not have enough resources to accept all of the demand, so we have to say yes to 80% of the customers, and we have to say no to the remaining 20% of the customers, right? So in this case, you might say something like, we are sorry, we do not have enough people to handle all of the orders, so please come back the next day, right? You don't want to lose your customer, so you encourage them to come back. So in this case, right, we fall in the second scenario. We do not have enough demand capacity, so we only accept 80% of the demand. By the way, what we are doing here is also very similar to part 3 of the project. In part 3, you need to do everything in Excel, okay? The homework question 24, you don't have to do that in Excel, but for the project part 3, you need to do this in Excel. So in that case, let me give you the equation in Excel so that you can find the DAR. In that case, the DAR equals, so either 100% or the 80%, right? So in that case, we have to find the minimum between 100% or below 100%. And the number below 100% equals 1 divided by the maximum among the IUs. It might look technical, but actually this equation is a sum up of these 2 scenarios. Either we accept all the demand, or we can only handle partial of the demand, right? That's why we have these 2 terms here. And in the second term here, we take 1 divided by the IU of the bottleneck. So this is 1 divided by the maximum among all the IUs. Right? It is the same thing. These and these are the same thing. It's just a way how to specify the equation in Excel for it to work, right? So that's how we find the DAR, the demand acceptance ratio. So the bottom line here is, in this particular example, we can only accept 80% of the demand. So let's continue with our work. Going back to the table. Again, for you, you just simply make your table longer. For me, I have to do the frame. Okay, so we have station 1 right here, 2, 3, 4, and 5. And then we reserve the biggest column for the names of the values, right? Why do I always go slanted with this column? Let me try it one more time. Okay, so the next things that we calculate is called the effective or the flow rate. All right, so this is a flow rate of the ice cream, right? So in this line, we calculate the number of ice creams going through per day. So how many ice cream will go through the first station, right? How many of them will go to 2, 3, 4, and 5? That's the calculation here. At station number 1, originally we have the demand of 40 ice creams, right? But then because we can only handle 80% of the original demand, so I would take 40 times with 28. Right? It tells us how much of the original demand that we can accept. So that's why we have 32 here. Right? The customer orders 40 ice cream, but then we do not have enough people. In real life, not enough people or enough ingredients, right? So that's why we cannot have 32 ice cream. 40 ice cream. Instead, we can only serve 32 ice cream. In the same way or by the same token, we're gonna calculate that for 2. So we take 40 times 0.8, we have 32 ice cream going to the second station. And then 32 through the third station. And 4 is a fire. No ice cream will go through it, right? So how to calculate this number? We have to take 0 times with 0.8, not 40 times 0.8. Because at station 4, we know that no ice cream will go through. So you have to write out that 0. And then 80% of them go through. Then of course, 80% of 0 is 0. Right? But in terms of the equation, it has to be 0 times 0.8. It cannot be 40 times 0.8. Conceptually, that will not be correct, right? So no ice cream will go through the fire, and we scale that out to have only 0.8, then it's going to be 0. By the way, because in project part 3, you need to do this all in Excel. That's why at that time, you're going to be very specific about what cell times with that cell, right? Even though there are many zeros in the table, but you need to choose the right 0 to multiply that with 0.8. All right, so then the last one is we just go back to the 40 times 0.8, and that's how we have 32, okay? So in one day, these are the number of ice creams that actually go through the kitchen, right? 40 is too much. Only 32 actually go through the kitchen. Right, so that's a flow rate of A. And then we have the flow rate of B. Of how many B's a day? So in the second one, right, let me remind everybody that we have 50 burgers. That's the original demand. Today, the customer ordered 50 units or 50 burgers. I would like the whole class to try it and share your answers for the whole row. So, or in other words, please try these 5 numbers, and then please share these 5 numbers in the chat window. Okay, so what will be the answer here? What will be the answer here? There, and there. Please feel free to share. Okay, so I got that first from Phelan. I don't say Phelan is right or wrong. I would like everybody to try and share if you can. Okay, Christopher and Alita, Sophia. so all of you got the same thing, huh? Okay, so you know what? Actually, all of you got it correct, and then Solin also got the same thing. Good. Yeah, you're all correct. In that's only for one, right? You need to go through the whole row. Yeah, but 40 is correct. Okay, good. All right, so we got 50 times 0.8. Why? Because we cannot handle all the demand. So now we can only accept 80% of the original demand. By the way, do you see that if we multiply everything with 0.8, then we keep the proportions among the ice cream and burgers the same, right? Earlier it is 4 divided by 5, then here we also have 4 divided by 5, or 4 to 5. So we have 40 over here. And then the second one, by the same token, we're gonna have 40 burgers going through resource number 2, right? It's just not merely how many burgers that the customer orders. Here we write out how many burgers that require work out of each of the station, right? We do not say that lengthy explanation here, but please keep in mind that's the meaning of what we do here in this part of the table. All right, so 40 ice cream requires works out of station 2, and that's correct. So station 3, because no ice cream will go through, no burgers will go through the ice cream machine, so we have that 0. And then, of course, when we scale 0 down to 0.8% or 0.8, then it's going to be the same, right? 0. And then we have 40 again here and 40 again here. Right. Now let's go to the third products. So the flow rate of the fries. How many fries per day? By the same token, it's easy for you now. So let me work on this with you. Originally, the demand is 60 units per day, but then we can only honor 80% of the demand, right? So we multiply that 60 with that 0.8, and then we have 48, right? So earlier we talked about 40 divided by 50 divided by 60, and now we have 32 divided by 40 divided by 48. But then the proportions are the same as before, right? So we assume that the proportions among the dishes are the same like before. And then everything here is 80% of the numbers that we got earlier, right? So 48 units of fries require work out of station 1. Those 48 units of fries also go to station 2. And for the third station, we have 0 times 0.8, right? So we have 48 too. I'm sorry, from 0. Matthew, let me go back to the previous slide and then you're gonna see that. Okay, so the 0.8 is right here, right? We take 1 divided by the implied utilization of the bottleneck. Or in other words, we take 1 divided by the highest IU that we find. Okay, we take that, and we have that 80%. Right? So I hope, okay, good. Let's go back to the calculation. So that's what happened at 3, and at 4, we're gonna have 60 times 0.8 again. That's how we have 48 again, and then 48, all right? So those are the number of physical units that require work out of each of the stations. But again, with ice cream, with burgers and fries, we cannot add them directly, right? That's why I would like to remind everybody that in this case, we would use a common flow unit. to be the minutes of work. Right? So we would convert all of the physical units here into the minutes of work. So for the first one, I would write that out as the workload, the effective workload. Previously, like last Wednesday, we call it as a workload, right? But here we talk about the effective workload, how much workload is actually applied to each of the station, right? So in this case, when we talk about the effective workloads, then the units is not ice cream anymore. The units is how many minutes of work are required per day, right? So at station one, we if we look at the table, the first part of the table, we see that it takes 5 minutes to process one ice cream through, right? And in this case, we calculate the number of ice cream actually going through is 32. So we multiply per each with the 32 ice cream, right? And for the second station, it's very similar. We would, but then again, let me look at the table. It takes 3 minutes per ice cream, and then we have 32 ice cream. So we multiply them together like that. For the third station, it takes 15 minutes per ice cream, and then we multiply with 32, right? The fourth one, you know what? It is 0 times 0. What is the first 0 and what is the second 0? The first 0 comes from the processing time. It says here that because the ice cream doesn't go through the fourth station, so it takes 0 minutes, right? Because it skips station 4, so it means that we have 0 minutes for each ice cream. And then because there's no ice cream going through, and this 0 is coming from that 0. Okay, so that's why it's 0 times 0. And then the next one is we have 6 minutes times 32. So if you just look at the processing time in the technology part of the kitchen, the restaurant, you see that it takes 6 minutes per ice cream. So we multiply that with the 32 ice cream that we have here. Again, we have to be very specific because if you work on this question in Excel, right, you have to know which cell multiply with which cell. All right, so we have the effective workload from A, just multiply it out, then we have 160 here. And then we have 96, then 480, minute 0, and then 192, right? So these number means the following. The workers at station 1 actually spend 160 minutes on the 32 ice cream, right? At station 2, the workers spend 96 minutes, actually spent 96 minutes on the ice cream, on those 32 ice cream, right? All of these are for the ice cream. The actual minutes of work or the actual work time to cook the product A through. By the same token, we're gonna find out for the effective workload for the burgers in terms of how many minutes per day. I would like you to try the first number in the line, only the first number, okay? So what should we write here? What times what equals what? Just feel free to share. So yeah, because now I would like you to relate the numbers in the table together, right? The table might be big now, but then I hope you know how to relate them together. I got the first answer from Ferran and Christopher VE. Right. You are all good so far. Okay, Elida, Nguyen. There's something that my computer. Okay, so yeah, I believe that everybody gets it right. So we would take post station number 2, right? I just look at the table right now, and it takes 5 minutes per burger, and then we multiply that with 40, right? The second one we take 4 minutes for each times with 40, and then we have 0 times 0 because the burgers will skip the ice cream machine, right? And then the next one is we take 3 minutes per burger times with 40 units. And then finally 6 times 40. So we got the following numbers, right? 200, 160, 0, 120, and then 240. Right? So now you already know how to relate the numbers together. Let me work on the C with you. The effective workload of the fries in terms of how many minutes of work per day. Okay, so we'll just look at the table to know the processing time. It takes 5 minutes at 1. And because there are 48 units going through, so we multiply that with that. At station 2, it also takes 5 minutes. Multiply with 48. Okay, so Alita already got it. Oh, do I forget it? Oh, sorry. Thank you. Thank you, Elita. Good. Okay, so for 2, we have 5 times 48, and then the next one we have 0 times 0. The next one, if we look at the table, right, it should be 3. Okay, 3 minutes per fries, but because we talk about 48 units of fries, right, we multiply them together, and then 6 times with that 48. And here are the answers, the numbers. We have 240, and then again 240. The third one is easy, it's just 0. Oh, by the way, I forgot to change the color. 240 here, 240 here, 0, 144, and then 288, right? Even though it looks like a lot of calculation, but I hope you see the logic behind this. It doesn't, it is not as difficult as it seems to be. I would say it's not that difficult at all. It's just the concept behind the numbers are the things that we need to really grasp here. All right, so so now we already convert. So what we just did is the following: we just convert the physical units, right, into the minutes of work per day. Because the reason is just simply because we cannot add 32 ice cream with 40 burgers and 48 fries to say this is a total demand. It would be wrong to say that, right? Because the units are different. So that's why now we convert everything to the minutes work. so that we have the same units, and then we can add them up, and we can proudly say that, oh, this is a total minutes of work required. Okay. So with that, now the next logical step is we add these three numbers together. 160 plus 200 plus 240 will be 600 minutes, right? The next one is 96 plus 160 plus 240. That will be 496. On and on, right? The third one is easy because you take that 480 plus that 0 plus that 0. In the reality, you will see zero, multiple zeros somewhere in the table because some products will skip some steps, right? Okay, so let's add them together and then think about what to do with it. So let me continue with our table, and we are quite done. We are actually quite at the end of the table. You know what? I really want to test you this in the exam, but it's so long, and that's why I will not test you this in the exam, right? And instead, I ask you to do this in the project when you and your partner will have more time to work on it. By the way, I'm sorry that I did not have the chance to finalize the groups yet. So if you do not have a group yet, I will need to work on that for you. All right, so we have station 1, 2, 3, 4, and 5. And we reserve the day column here for the variable names. Okay, so let's have the next one as a total effective workload. In terms of how many minutes per day. Okay, so station 1, we just add the three numbers together. Then we have these 600 minutes. Does anybody have a question about it? I hope you know how to get the 600, right? We have three products ABC, so we add them together, then we have the total effective workload. Again, we call it as effective because this is the actual amount of work going through, right? At station 2, we have 496. Station 3, 480. At 4, we have 264. And at 5, we have 720. Right, we just add the numbers together. Yeah, Matthew, that's correct. We just add them together. Okay, so so after we add this, we have now we know that in one day the workers at station 1, no matter how many workers, it doesn't matter. They would have to work for 600 minutes per day. The workers at station 2 would have to work for 496 per day. And then 3, and then 4, and then 5, right? So earlier, you know what, we called it the DAR. We scale all the demand out to 80% of the original amount, right? Then definitely the smaller demand should go through the process, should go through the kitchen because it is not as much as before, right? But to check, to verify that we can actually handle the demand, the new demand, to verify that we have enough capacity to handle the new demand, right? Then we will need to calculate the IU one more time. So we calculate the IU as the workload or the demand divided by the capacity. Right. I would like you to try it. So to calculate the IU of station number 1, what number divided by what number? Please feel free to say your thought in the chat window. to find the IU, then what number do we take divided by what number? I got the first answer from Christopher. So IU is a workload divided by the capacity. Right. Okay, good. So see, I also got you also got the same thing. Yeah, that is correct. I hope and I believe that other people, I mean other students also see the same thing, right? So in this case, the capacity of station number 1 is 960. And then the workers over there are required to work for 600 minutes. That's why we calculate the total effective workload, right? So we take the workload of 600 minutes divided by the capacity of 960. And then at station number 2 is quite similar, right? We take 490 60 minutes. Oh, I'm sorry, 496 minutes required work time divided by the capacity of 960. At station 4, we have 480 divided by 480. Right. At station 4, we take 264 divided by 480. Again, the 480 here are the capacity because there's only one worker each at 3 and 4. So in one day, that's how many minutes of work that single worker can offer, right? So we take the workload divided by the capacity, workload divided by capacity. At 5 is very similar. We take 720 divided by 960, right? And here are the answers, the final numbers. So, Phelan, we scaled out the demand with the hope that we have enough capacity to handle the smaller demand, right? So we calculate the DAR for that purpose. But we need to verify that we do have enough capacity to handle that new demand. So that's why we calculate the IU one more time. To verify that the smaller demand is okay with our capacity. And you're welcome. So let me write out the answers for you. The first number is 62.50 cents. The second one is 51.67%. The third one is 100%. The fourth one is 55%. The last one is 75%. Right? Okay, so it says the following. Now we scale the demand out to be 80% of the original demand. Then the new demand or the new workload at station number 1 is 62% of the capacity of 1. The new demand is 51% the capacity at 2. The new demand is 100% the capacity at 3. And at 4, 55% and 75%. So we do have enough capacity to handle the demand at 1. We have more than enough capacity to handle the demand at 2, 4, and 5. And we just have enough capacity to handle the demand at 3. 100% means what? Workload equals capacity, right? So we just have enough capacity to handle the demand or the workload at 3. So that's the meanings of this number. Is that 100% a coincidence? I hope your answer will be no, right? Because earlier this number is 125%. So if we cut out the 25%, then we're going to have the exact 100%. That's why it's not a coincidence to have this number, right? How do we cut it out? We take 1 divided by the 1.25, then we're going to have 80%. So
I can understand. Can I understand this way? This IU here probably is the reality utilization. It's not exactly IU, it's like U.
you're right. Yeah. IU is just telling us the demand pressure, right? So that's why we take the workload divided by the capacity. Earlier is not exactly U yet, because earlier we know that, let me go back here. At this point,
So here is exactly U.
This is the IU, right? It's not the IU yet, because at this point, we are not quite sure if our restaurant has a capacity to handle the demand or not yet. So that's why earlier we just calculate the IU, not the U, so that we know what is going on. Do you see that, C2? I mean,
Yeah.
I'm sorry, C. Okay, good. Okay, yeah. All right. Yeah, so earlier we find out that the IU here is 125% exceeding, right? So the demand exceeds the capacity by 25%. So we try to cut that extra 25% off, right? And that's why we go here and we hit exactly 100%. I hope you see that is not a coincidence, right? All right, good. So the next step is so now we already verified that we have enough capacity to handle the demand, right? All the IUs either less than 100% or equal to 100%. Now, because it works now, so we can actually calculate the utilization. Utilization equals the flow rate divided by the capacity. Okay, so I would like you to pause a little bit, think about it. How to calculate the utilization in this case. Please try that for the first station. What number divided by what number? Right. Please think about it. So for station number 1, what will be the capacity you use? What will be the flow rate that you use, so that we can calculate the utilization of resource number 1? Here is a hint for everybody. Just think about, so we have 100 rooms in our hotel, and we are renting out 80 rooms, right? Then we take 80 divided by 100, then we're gonna have the utilization, right? So in this particular example, how would we calculate the flow rate divided by the capacity? For station number 1 only. Try that for 1, everything else should be the same. Right? So what would be the utilization at 1? What number divided by what number? Got the first answer from Philip. Elita, that's correct, Elita. We talk about the same thing, right? Otherwise, the units of the flow rate and the units of the capacity have to be the same for us to make that division. So what number divided by what number? let me confirm that the capacity here is 960 minutes, right? So if I write out the equation, then this 960 minutes of work per day, that's the capacity of the resource number one. So now you need to think about what would be the flow rate, right? I don't say Berlin is right or wrong. I would like to have more thoughts from you. So what would be the flow rate here? I know the table has a lot of numbers right now, but at the end of the day, think about this as we have 960 rooms in our hotel. That might be a very big hotel. So how many rooms in the hotel that we are using right now, right? That's the question. Okay, so you know what? Actually, oh, I got another answer from Christopher. Anybody else? Okay, so both. Okay, so yeah, you are correct. So I got the answer from Phelan earlier, and now Christopher, and then Stalin. Yeah, you are correct. So out of those 960 minutes that the workers can render, they are actually work for. That is correct C. In this case, U equal IU. Okay. So we have that 600 divided by that 960. And by the same token, we're going to have all of the others kind of similar to what we have in the IU row, right? So 496 divided by 960, and then 480 divided by 480, and then 264 divided by 480, and then 720 divided by 960. Is that a coincidence that U equals IU in this case? The answer is no. It's not a coincidence, because earlier we just verified that. That's why we have to do that verification. We just verify that demand is either smaller than or equal to the capacity, right? So whenever demand smaller than or equal to the capacity, then U and IU are equal in terms of the value. Let me remind everybody that U and IU are two different concepts. One is about efficiency. One is about demand pressure, right? There are two different concepts. But whenever demand is smaller than or equal to capacity, then the two values are equal. So that's why we have that equal here, equality here, equality here, equality here, right? So let me write out the values for you. 62.50%, 51.67%, then 100%, 55%, 75%, right? It's not a coincidence that U and IU are equal here, because earlier we do a very crucial step. We say that we only accept 80% of the demand. So the new demand is kind of pre-calculated so that they can go through, right? That's why demand is smaller than or equal to demand, right? This slide you confirm that, and that's why the right on the two values are equal. So that's the concept, right? It's not the calculation. The logic here. All right, so that's the end of the table, and the rest we need to draw a picture to see what to do with it, right? Let me do it quick with you. So next we draw the utilization profile, so that we can look at the usage and efficiency. Right? We ask ourselves if we are efficient or not in this case. So we lay out the resources horizontally. And then on the vertical axis, we're going to show the utilization, right? So we show the U on the vertical axis. And to draw it effectively, we should always have the 100% to draw it, to read it effectively. Then the first station is about kind of 62%. I need to draw it a little bit higher. Right, 62% right here for resource number 1. And then 51% for resource 2. At 3, we have exactly 100%. That's a bottleneck, right? And then 55%. And then 75%. Okay, so again, we look at the U profile to see if we are, how much we are using, if we are efficient or not, right? The quick answer here is it's not efficient because we are using only 60% here, then the remaining is the waste. We are using 51% here, then we also have the waste here. But the bottleneck, we are not wasting anything because we are using 100% of our capacity. But then going back to 4, we are wasting something here. And at 5, we are also wasting something here. So actually, if we look at this picture, then the process is not efficient. Even though we hit 100% of the bottleneck, but that's only for the bottleneck. For the remaining of the process, we are not efficient, right? Because we see the waste. The second bad thing about this picture is the process is not balanced. It's not balanced, right? So the implication here is the following. We are quite done. Number 1, we need to balance out the process. And number 2, we need to take demand in, take more demand. And then promote if necessary, so that we have more demand, right? So how to balance out the process? There are 2 things that we have to do. Number 1 is we need to cross-train the workers. Like we discussed in question 23, right? And then the second one is you need to reassign the workers or reshuffle the resources to be a little bit more general, right? So that we have got the workers can flexibly working in your system like water. So when you pour water in a vessel, then it's gonna even out, right? And then we take more demand, then all the columns will go back up, back up, back up, and all the columns will hit 100% at the same time. So in the end, we have 0 waste everywhere, and then we are totally efficient, right? So the last line of the table, the long table, but the last line is very crucial for you to manage your business. Okay. So I'd like to thank you all for joining me today. On Wednesday, we're gonna cover question 25, and you should be ready with the remainder of the homework. Thank you, and have a great rest of your day, and see you back in the morning. All right. Thank you all.